So as I promised, we are starting with individual air handling unit, different types of air handling unit which we have. And so for your information, there are 5 types of air handling units. Sorry, there are 4 types actually. The 4 major and common types which I'm talking about. And then there could be multiple different modifications made to each of those, and there could be n number of different types which we have. Otherwise, like if we look into different buildings, we can have maybe infinite different types of air handling systems, because we make a small change and it could be a new type. So, but there are 4 common or 4 major types. And the first one which we are going to cover is SDCAV and terminal reheat, which is single duct constant air volume terminal reheat. So I hope you have understood the different categories which could form. So I have said this as single duct, constant air volume, terminal reheat. So there could be another possibility of having 2 ducts. So there could be dual duct. So that is the first point of differentiation. And the second point of differentiation is this is a constant air volume. The other possibility is having a variable air volume. So the 4 major types would be: the first one, single duct constant air volume; the second one, dual duct constant air volume; the third could be single duct single duct variable air volume; and fourth, dual duct variable air volume. And in the 4 separate videos, I am going to cover each of these 4 systems. But for this video, we are going to start with the first one, which is single duct constant air volume. And for each of the videos, each of these different types, I am going to cover the basic structure of the air handling unit and all the calculations which are to be done. So let's make the structure first. And I am usually going to follow what is covered in most of the courses which are taught in graduate school. So we start with the outside air, and maybe we have some return air coming. So this is going to be the return air, and the leftover is exhaust or relief air. Now this outside air is mixed, so this becomes a mixed air. MA is a mixed air notation. The mixed air goes to a preheater, preheating coil, which then later goes to a cooling coil, which later goes to, so the air is flowing in this direction to the fan, and from the fan we may have a reheater which supplies air to the zone, and from the zone we have the air coming back to the as a return air. So this is our zone. This is the zone of the building which I am talking about. That's the room maybe, or there is some area of our building, right? Now let's write out some notations. So this is the mixed air location. This is preheat coil exit location, which is noted as PH. This is CC, so cooling coil exit. This is supply fan. This is reheat or reheating coil. And we may have another fan over here, which is return fan. It is all optional. We can have a cooling coil after the supply fan, or return, we may have a return fan or we may not have a return fan. They are all optional. It depends on the requirement, everything. This is the general structure of an SDCAV, which is a single duct constant air volume. So it's a single duct, which looks like we are having a single duct for the supply. And terminal reheat means whatever reheating which is required will be done at just outside the zone, just at the entry of the zone. So now what our aim is, we want to maintain a constant temperature in the zone, which is Ti. Interior temperature of the zone should be remain constant. And from the SCAP analysis or the steady state building load calculations which we have done earlier, we'll have the total amount of sensible load and the latent load of the building known. So from the zone we must calculate the total sensible and latent load. You could also be given the values of sensible and latent load, which are notified as Q sensible or QS, Q latent or QL, right? This temp and the temperature of the zone which is required. That's the comfort temperature which we want inside our zone. Based on these values, my supply, this is the supply location, and the temperature of my supply should be calculated. How's the calculation done? Based on very simple heat transfer and heat balance equation. So what we have is the Ts should be Ti minus Q sensible upon 1.08 Vi. How the 1.08 comes is what I am going to explain you. When I do a Q sensible, we'll have rho Vc, that's a kind of UA, equivalent to UA, right? Or let's go from very much basic so there's no confusion at all in your understanding. So when I do a Q is mc delta T. That's the very basic equation. The amount of heat transfer or heat loss will be mCp delta T. Mass can be written as rho, and if we want to find out the rate of heat transfer, we'll do m dot and q dot, right? So my q dot becomes rho v dot, that's the volume flow rate, into C into delta T. From this equation, my delta T will be Ts minus Ti, and rho v C. So the rho of air should be used, C of air should be used, and the rho usually V dot in the standard units is measured in feet cube or feet cube per hour or feet cube per second, or my the SI units could be my meter cube. But if we want to use the V dot, so V dot if it is in CFM, which is one of the standard units or standard measurement system for my air handling unit, then if we convert all these units and consider the values of rho of air, which is 0.074 in imperial units, and C of air, which is 0.02 I guess, or 0.2 something, then if we convert everything, we'll have 1.08 V dot in CFM, V dot in CFM, and delta T in degree Fahrenheit. So using this equation, I am forming this equation which gives us the value of supply temperature. So that's the temperature of our air which should be supplied to the zone. Now after the cooling coil, so cooling coil is usually set up for a fixed cooling coil leaving temperature. So I can have my cooling coil leaving temperature set as 55 degrees Celsius, 55 degree Fahrenheit, and at that I'll have a humidity of 90% relative humidity. So this location, temperature and relative humidity are fixed. Now the supply fan, because the fan is rotating and it is pushing the air, there will be a small rise of temperature through the fan, and that is called as supply fan temperature rise, delta T SF. Supply fan temperature rise, right? So my this location temperature at this or this location is the same, will be, so let's say the temperature of the cooling coil will be TC, cooling coil TCC, and this temperature will be TCC plus delta T SF. Now we want to compare if my supply temperature which I have calculated from this. So over here we have all the values known, the supply flow rate, because it is a constant air volume. My flow rate V dot is known to us. Q, that is the loads which we have already calculated. The temperature which we want to set in the zone is already given to us, or we know that we want to maintain the zone at 75 degree Fahrenheit or 72 degree Fahrenheit, and hence from that we have a value of TS, supply temperature, and TCC is the set point temperature, and delta TSF can be again calculated. So that calculation is based on work, the power of the fan, and divided by some factor. Let's look at the factor value. .08 into V dot, that is the delta TSF value. So if my fan is using some given number of watts, maybe the W dot is in BTU per hour, and V dot over here in this formula is in CFM, because I have already done the conversion based on this rho VC. From there my 1.08 value is coming. So if I have a fan which is using 100 watts per BTU and a volume flow rate is given as some 1000 CFM or 10,000 CFM, I can calculate the value of delta TSF. I already have the value of TCC plus delta TSF will be compared. So now if my TS is greater than delta TSF plus TCC, then reheat is required. And how much? What does that mean is, I am having a very cool air. So if the TCC is usually 55 degrees Fahrenheit and delta TSF usually comes out to be 1 to 2 degree Fahrenheit, and my TI is usually 72 degree Fahrenheit, then my delta TS will be some 68 degree Fahrenheit maybe, or 66 degree Fahrenheit. I am just taking some random numbers for you to understand it more better. So using this, what I am comparing is, I want to supply it at 66 degree Fahrenheit, but it is greater than my 57 degree Fahrenheit. This location having an air of 57 degree Fahrenheit, while I want to supply it at 66 degree Fahrenheit. So what my reheating should be, my reheater should heat the air from 57 to 66 degree Fahrenheit, and that's the process of reheating. So reheating energy used will be 1.08. Again, the 1.08 is coming from this value, rho VC, 1.08 into V dot into delta T. Over here the delta T will be 66 minus 57. That's the amount of reheating energy which we want to supply, or that's the amount of energy which it will consume over there. Now we have these temperatures, we have this temperature. Now the return temperature is there. That's the temperature of the air which is coming out of the room. It could be from the exhaust ducts or from the cracks or the leaks from the windows and from the door. So the return temperature depends on two things. If there are some exhaust air from going away or going from the light fixtures, then because of the light fixtures which are heated up, the return air will get some more heat. So there could be some reheating or return air heating. But if we ignore that right now, then the return temperature of my air which is going out will be equal to the temperature of the zone, right? And the temperature of the zone is Ti, which is known to us. Now after the Ti known, that's the same temperature which is coming of the air which is over here. That's the ideal case when there's no frictional heating in the ducts. We are assuming everything ideal right now, and that's equal to the return air temperature. And that's equal to the return air temperature which is coming over here. The outside air temperature and the relative humidity will be known to us. That's based on the measurements which we do using the sensors. So for the mixed air, what the condition we have right now is, for mixed air, it depends on the amount of outside air which we are using. So let's indicate the amount of outside air as XOA, which is the volume of outside air divided by the total volume, and my total volume is VOA, that's the outside air volume, everything is rate based, plus the return air volume. So return air volume is what is coming from here, and some is exhausted over here and some goes back. So this is the return air volume which is mixed up with the outside air, and I have a total volume which is circulated inside my coils and my zone. So using this formula, what we can do is, my temperature of mixed air can be calculated using energy balance. Very simple energy balance could be done. That's the mass of mixed air into temperature of mixed air, mCp delta T. Mass of mixed air is equal to mc delta T of outside air plus mc delta T of return air. Using this expression, what I can find is, my temperature of mixed air will be equal to temperature of return air plus XOA into temperature of outside air minus temperature of return air. I'll prove this formula later, but as of now you can take this formula as granted to find out the temperature of the mixed air. From the temperature of mixed air, we move forward towards the next step. So we have this temperature of mixed air calculated now. Now the preheater coil is for the purpose of not letting the coils, the cooling coils are having a very cool temperature. If the air goes in which is very cool, which is already very cool, then the cooling coils might freeze up. Might freeze means it can go below 32 degree Fahrenheit or below 0 degree Celsius, and it will ice. All the water inside my coils can ice up, and I'll have all freezed, all packed, all solid, and that will lead to cracking, that will lead to bursting of the coils, because as the water cools, the density of the water reduces, and because of that the water expands. As the water inside my pipes, inside the coils of my cooling coil expands, it will obviously lead to the cracking of the coils, right? So we want to supply the air which is greater than 32 degree Fahrenheit, and it should be greater than the cooling coil leaving temperature also, because if it is lesser than cooling coil temperature, then it will start cooling the coils. So my preheat coil, what's the purpose is, if my mixed air temperature which we have calculated over here, if that mixed air temperature is less than cooling coil leaving temperature, this 55 degree Fahrenheit, which is the usual case, then it will preheat. Then it will preheat air. That means it will heat up the air from whatever TMA which we have to 55 degree Fahrenheit. If it is not the case, that means if my TMA is greater than 55 degree Fahrenheit, then air will just pass through this preheating coil doing nothing, and then from the cooling coil, what we have over here in the cooling coil, we'll have cool water coming. So chilled water will be supplied, and the chilled water will be returned back. And when the chilled water supply and return back happens, it is a kind of heat exchanger. The cooling coil is a kind of heat exchanger. So when the cooling coil chilled water is coming, it transfers heat with respect to that outside air which is flowing over here, and the supply water is coming over there. So the supply water, chilled water, maybe it is at a temperature of 45 degree Fahrenheit and the outside air is coming at some 65 degree Fahrenheit or 70 degree Fahrenheit, then the outside air will get cooled to 55 degree Fahrenheit. That is set to for the cooling coils to operate with, and the return water will be, maybe it will heat up from 45 degree Fahrenheit to 50 degree Fahrenheit, and that's how all the circulation happens. So in this process we have calculated all the important temperature values based on the given contents. Given values would usually be the loads and the temperature and the volume flow rate inside our air handling unit. So this is one of the very basic. Still it is not complete. We need to do a lot of analysis in this SDCAV also, but as of now we have given a complete picture of it and all the procedure of doing all the calculations. In the next video we'll do more detailed analysis of this air handling unit and continue with other major air handling unit types also, which I have explained in the start of the video. Thank you.